Hello, viewers. In today's session, we are going to discuss an important and conceptual problem from derivatives. And here we are going to solve this problem where we are given a function f of x which is equal to e raised to a maximum of x square comma a fractional part of x for all x belonging to the interval that is 0 comma 1. So here 0 is included and 1 is not included, and we have to find the derivative of f of x at x is equal to half, right? So let us see how we can solve this problem using the concept of maximum of two quantities a and b. So now let us consider two quantities a and b, right? And the maximum of the quantities a and b is defined by this expression, that is half and a plus b plus mod of a minus b, right? So here we'll first simplify or modify this function f of x using this result. So here we have maximum of x square and fractional part of x, right? So here we can write maximum of x square and fractional part of x using this result as half, and then we can take a is equal to x square and b is equal to a fractional part of x. So we have x square plus fractional part of x, substituting the values of a and b in this result, and then we have a mod of x square minus fractional part of x, right? So now we have to simplify this expression, and here we'll make use of the definition of fractional part of x in terms of greatest integer function. So the fractional part of x is defined as x minus greatest integer of x. So we can now write half, and here we have x square, and for fractional part of x we can write x minus greatest integer of x, and then here we have x square minus fractional part of x. So here multiplying fractional part of x by negative sign, we have minus x, and then we have plus greatest integer of x. So now we have here this interval, that is x belonging to the interval 0 comma 1, that is x is greater than or equal to 0 but less than 1, right? So whenever x lies between 0 and 1, then the greatest integer of x is always going to be 0, right? So this is an important step here. So replacing greatest integer of x by 0, we have half, then we can write x square plus x minus 0 plus mod of x square minus x plus 0, and we can now write half x square plus x plus mod of x square minus x. So now to simplify a mod of x square minus x in this interval, let us make use of the definition of mod function. Now the definition of mod function is the mod of p is the positive p whenever p is greater than 0, mod of p is 0 whenever p is equal to 0, and mod of p is negative p whenever p is less than 0. So here we have a mod of x square minus x. So x square minus x can be written as x times x minus 1, right? And now see here x lies between 0 and 1, right? So all the values of x which lies between 0 and 1, it makes this quantity, that is x minus 1, as a negative quantity, right? Because whenever we take x lying between 0 and 1, including 0, then x minus 1 is always going to be a negative quantity, but x is a positive quantity. So here we can write positive times a negative, so this becomes a negative, right? So x square minus x is always going to be less than 0 for all x belonging to this interval, that is 0 comma 1, right? So using this definition of mod function, we can now write mod of x square minus x is equal to a negative of x square minus x whenever x square minus x is less than 0, right? So now replacing mod of x square minus x by a negative of x square minus x, that is minus x square plus x. Now a maximum of x square comma a fractional part of x, it becomes half, and here we have x square plus x, and mod of x square minus x is negative x square plus x, right? So now simplifying it, these two quantities get cancelled and we have half and x plus x. So this is half and x plus x is 2x. 2 and 2 get cancelled and we are left with only x, right? So this quantity, that is maximum of x square comma fractional part of x, is equal to x. So now our function f of x can be defined as e raised to maximum of x square and fractional part of x, which is equal to x. So here we have x for all x belonging to the interval 0 comma 1. So now what we have done here, we have modified this function using the concept of maximum of a comma b, using this result. So we have f of x is equal to e raised to x. So if we differentiate it, then f prime of x is d by dx of e raised to x, and the derivative of e raised to x is e raised to x, and we have to find f prime of x at x is equal to half. So taking x is equal to half in this expression, we have f prime of half is equal to e raised to half, right? Which can also be written as square root of e. So the derivative of f of x at x is equal to half is equal to square root of e. Hello viewers, in today's session we are going to discuss another important and conceptual problem from definite integrals, and in this class we are going to evaluate this definite integral that is from minus 2 pi to 2 pi, and here we have a mod of 2 pi minus a mod of x and dx, right? So let us see how we can easily evaluate this definite integral by using two concepts. The first one is the definition of mod function, and the second one is the property of definite integrals, right? So let us start, and let us first call this integral as I, right? Now see here the limits of integration are from minus 2 pi to 2 pi, right? And the integrand is say the integrand is f of x, and it is mod of 2 pi minus mod of x, right? So here first of all we'll make use of an important property of definite integrals, which connects the concept of even functions, right? So here we have minus a to a, and we have a function say f of x dx, and the value of this integral that is from minus a to a f of x dx is equal to 2 times the integral from 0 to a f of x dx, provided this integrand, that is this function f of x, is an even function, right? So a function is said to be an even function if f of minus x is equal to f of x, right? So if we replace x by minus x in this function f of x, and the function remains the same, then the value of this integral, that is minus a to a f of x dx, is equal to 2 times the integral from 0 to a f of x dx. So first of all, we'll apply this property to this integral, right? So here if we replace x by minus x, then we have f of minus x, and here we have mod of 2 pi minus mod of minus x, and we know that a mod of minus x is equal to simply mod of x, right? And here we have mod of 2 pi minus mod of x, and which is simply the function f of x, right? So we can see that our integrand mod of 2 pi minus mod of x is an even function, right? So we can now write this integral I as 2 times the integral from 0 to a, and here the value of a is given by 2 pi. So we have 0 to 2 pi, and here we have simply a mod of 2 pi minus here we have mod x and dx. So now we have to evaluate this integral, right? And here we can see that we have a mod of 2 pi minus mod of x, right? So let us apply the definition of mod function. Now see, a mod of x is defined as positive x whenever x is greater than 0. Mod of x is 0 when x is equal to 0, and mod of x is negative x when x is less than 0. And see, here the limits of integration are from 0 to 2 pi, right? So when x belongs to this interval, that is from 0 to 2 pi, then we have all the values of x as positive, right? So when x belongs to this interval, that is from 0 to 2 pi, then all the x are positive numbers, right? So mod of x must be equal to positive x because x is greater than 0. So here we can now replace mod of x by positive x. So we have 2 times 0 to 2 pi, and here we have mod of 2 pi minus mod of x is replaced by positive x. So we have mod of 2 pi minus x dx. So now we have to evaluate this integral 0 to 2 pi mod of 2 pi minus x dx. So let us again apply the definition of a mod function to mod of 2 pi minus x. Now see, x belongs to this interval, that is 0 to 2 pi, right? So whenever we take any value of x which belongs to this interval, then 2 pi minus x is always greater than 0, or in other words we can say that 2 pi minus x is a positive number for all values of x belonging to this interval. And when we take x is equal to 0, then we have 2 pi which is obviously greater than 0, and when x is equal to 2 pi, then we have 2 pi minus 2 pi, that is 0, right? And in that case 2 pi minus x is equal to 0. So we can now apply the definition of mod function. So mod of 2 pi minus x is equal to positive 2 pi minus x whenever 2 pi minus x is greater than 0, right? And mod of 2 pi minus x is equal to 0 when 2 pi minus x is equal to 0, and this is mod of 2 pi minus x is equal to negative of 2 pi minus x whenever 2 pi minus x is less than 0. So from this part of the definition, we can see that mod of 2 pi minus x is equal to positive 2 pi minus x when minus x is greater than minus 2 pi or x is less than 2 pi. Right. So whenever x is less than 2 pi, mod of 2 pi minus x is equal to positive 2 pi minus x, and our limits of integration vary from 0 to 2 pi, right? So now we can replace here this mod of 2 pi minus x as positive 2 pi minus x dx, and now we can easily find out the integral of 2 pi minus x. So we have here the integral of 2 pi dx as 2 pi x and x dx as x square over 2, and the limits of integration are from 0 to 2 pi. So now we can simply substitute the limits and we'll take the difference. So when we take x is equal to 2 pi, here we have 4 pi square, and then here we have 2 pi square, that is 4 pi square over 2. And when we take x is equal to 0, then both these terms reduces to 0, so we have 0 minus 0. So now simplifying this term, the value of this integral I is equal to 2 times, here we have 4 pi square, and here we have 2 pi square, right? And this is 2 times 2 pi square, that is equal to 4 pi square. So viewers, the value of this integral is equal to 4 pi square.